Hello everyone, in today's session we're going to talk about scanning a multidimensional array in an efficient way. Stay tuned. Let's suppose we are given a multidimensional array and we need to scan the elements to do some operations. How should we do that? In the first sight you may say that accessing to one element in a multidimensional array needs O of 1, then it doesn't matter how we scan the elements. This is true from time complexity point of view, but it's not true in the real computers. Let's see why this is not true. The answer of this question is that if the elements of the array is stored in the memory in a row major order, we have to scan the elements row by row, and if they are stored in the column major order, we have to scan them column by column. Why? It's because of two concepts, locality of the references and memory hierarchy. Let's see what are these two concepts and why they are so important. Special locality says when we fetch an element from the memory, we may need some nearby items very soon. For example, when you are reading a book and you open the book, with high probability you will read some pages before and after that. And when you open a picture and you want to watch a picture, with high probability you will watch some other pictures before and after that, right? And how the computer uses this concept in order to accelerate the processes. When we need a piece of information, it doesn't bring just that piece of information. Instead of that, it loads all of the block that the target information is in that block. The size of the block varies depending on the operating system, memory, and these kind of things, but it's usually more than 32 kilobytes. Now let's see what is the memory hierarchy. CPU, which is the central processing unit, is connected to the first level of cache, and it's connected to the second level of cache, and it's connected to the third level of cache. And the third level of cache is connected to the main memory, which is called RAM, and RAM is connected to the I/O controller in order to have access to the other sources of information like hard drive, CD drive, internet, and so on. As you can see, when we go far from CPU, the size of the memory increases, but the speed decreases because we have to bring the information close to the CPU, and when the data is in L1 cache, we can use it in the CPU. And what is the cache miss? When CPU needs some information, if it's not in the first level of cache, a cache miss happens in this level. And we have to bring the information from second level of cache into the first level and use it. And if it's not in the caches, we have to bring the information from memory to L3, L2, L1, and then we can use it in the memory. Now using these two concepts, let's assume that we are given these two-dimensional array, 256 rows and 256 columns. And we store the elements in a row major order in the memory, and remind the memory hierarchy, which is like this. Memory is connected to the L3, L2, L1, and the CPU. And in this imaginary example, let's assume that the size of the block is 256 bytes. It means that each row is stored in one block of information. If we scan the elements in a row major, we access the elements row by row. And if we scan the elements in the column major, which is like here, we scan the elements column by column. And let's see what is the difference between these two. In a row major order, we fix a row and then we scan all elements in that row, and then we go to the next row. In this example, the first element, we need the first element in the first row. It's not in the cache. Then cache miss happens here, 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 and then we will bring all the block to the L3, L2, L1, and the CPU will use the first element. In the next iteration, it needs the second element in the row, but it's already loaded and it's in the cache. Then CPU can use it very fast, and it can use all the elements in the current row. And when it's finished, it goes to the next row, but cache miss happens in this level. It goes to the memory, it brings the next block to the L3, L2, L1, and it brings all of the elements in the second row to the cache one, and CPU can use all of them. And in this model, we can see that for each row, we have one cache miss for each level of caches. And let's see what will happen in the column major order. In the column major order, we need the first element, and it's not in the cache. Cache miss happens 3 times, and we will bring the first block of information, and CPU will use the first element. And in the next iteration, it needs the first element in the second row, but it's not in the cache. Then cache miss happens 3 times, and then we will bring this block of information to L3, L2, L1. And it uses just one element of the loaded block, and then it goes to the next level. And we can see for each element we have one cache miss, and this happens also for the next columns, because remember that the caches have limited size and we cannot keep all of the elements in the cache. Then we replace them, and when we need this element, it's not in the cache anymore, and the cache miss happens, and we need to bring them again. And we can see for each and every single element of the array, we have one cache miss, and the total number of cache miss is more than 65,000, which is too much and time consuming. And this is why we should scan the elements in the same way that they are stored in the memory, which in this case is row major order. I hope you enjoyed. If you liked the video, please subscribe and share it with your friends, and see you in the next session.